Hey everybody, this is Horner, and here we go. We're going to look at centripetal force. We know that centripetal force goes round and round. Some things that you're going to need: pencil, paper, calculator. If you have those things, you will be set, and you can kind of help out a little bit here. That's probably the best way to do it, to make sure that you're active and working and make this time go a lot faster too. So one of the things that we're going to talk about today is circles. We're just going to start at the basics, talk about circumference and distance versus displacement of a circle. We'll do rotation very quickly and talk about time versus distance and what they can do. Then we're going to really get into the meat of things and look at speed and velocity, acceleration, the force equations. And I know that some of you are able to see some of the different force equations, roller coasters and flying pigs. So we'll take a look at those. And in fact, I think what we're going to do is we're going to change it. And instead of roller coasters and flying pigs, we're going to take a look at the centripetal force apparatus. That's a thing that you spin, and it will lift stuff because of the spinning, and then roller coasters. So we are not going to, I just got to make this change. We're not going to do anything with flying pigs. So if that's okay with you, maybe we'll do that another time. But we're going to do roller coasters, and we're going to look at centripetal force apparatus. It's kind of like Chick-fil-A in that it has CFA, but it really doesn't have much more to do with that. Alrighty, here's a circle. Okay, what do we know about a circle? A circle is round. Very good. A circle shows an infinite path. What do we mean by that? That means if I start here, I can just keep going forever, okay, or until I finally decide to stop. So how do we measure the distance that we travel along a circle? Well, probably the best thing to do is to start here, and then we start following the path of the circle this way. And if we get over here, we know that that is approximately, or it should be, 180 degrees. Or if I travel that far, we could also say that that is pi. So pi is really just the length of this arc. And we know that's approximately 3.14. So that is pi. If I go all the way around of the circle, that's 360 degrees, or 2 pi. So some people make jokes about that. They say if you go all the way around, come back and meet yourself again, it is pi or not 2 pi. So you can kind of think of it that way too. But what we want is we want to know what is the distance all the way around. So to do that, here is 2 pi, and we also can then take this, and what do we call this? This is the radius, and you can make it r, you can make it capital R, doesn't matter, just as long as we know that r is equal to radius. And if I take that radius and I multiply that by 2 pi, because 2 pi is all the way around the circle, then I get the circumference of the circle, and that is 2 times pi times r. So that's where the distance comes from. It comes from this math where we have 180 degrees is equal to pi, and we call that a radian. It's kind of weird. But then if we go all the way around, then we say that that is 2 pi in terms of the angle that we've gone. And if I want to know how far that is, I just use the circumference. So that's just 2 pi r. Now, the displacement is different. So the displacement would be if I started right here, okay, and I went to this side, it would actually be, displacement would be 2r. So if I start here and I travel in a straight line and I come over here, that is 2 times the radius. If I start here, and let's say I start here, go all the way over and come back, and that's my end, then that displacement would be what? So if I start here, go all the way over here and come back, or even if I go all the way around the path of the circle, what do you think that displacement would be? Because remember, displacement is final position minus original position. So what would that be? That's the question. Yes, very good. It is 0. And it's because if I start here and I end up here, I'm starting and stopping at the same place. So that would be 0. So that's not really much that you would need to know for this, but I would say that we really need to make sure that we understand that the circumference is the distance all the way around the circle, and we're not really worried about displacement. Okay, so let's take a look at the next slide. This one is about rotation. So if I go all the way around this, we said that if I make my path and I go all the way around the circle, we know that that is 2 pi, and the circumference would be r. How long does it take to get all the way around? Well, let's say that it takes 10 seconds, and let's say that the radius of this is 5 meters. And we want to know, well, first of all, how far did we go? So if you want to know how far you go, remember we use the circumference, and that's just 2 times pi times r. And so for this one, it would be 2 times pi times 5. And our time to go around is 10 seconds. Now, when we do rotation, when we think about circles, we don't really talk about the time it takes. We talk about what is, question mark, the period, okay? Period is equal to the time, so they're kind of similar, the time to travel one circle. And usually we don't say circle. Instead, we would say time to travel one rotation. So that's why we've got rotation up the top here. So if we go around one time, that would be the period. And so our period is 10 seconds. We know that velocity is equal to the change in position over the change in time. So what I'd like to do is let's go down here to where we have speed and velocity. And let's go ahead and find out what that speed is. So the speed is equal to, remember, change in position over change in time. But for a circle, we're going to call this tangential velocity. So we're going to put a VT here. And that's equal to 2 pi r, because remember, that's how far I go. And that is divided by the time it takes, and we call that period. Now, earlier we said that the distance from here to here, okay, so that radius, and let's go ahead and make this a big R. So we said earlier that the radius was 5 meters. So we're going to go ahead and put in R is equal to 5 meters. And we said that the period, T, is equal to 10 seconds. So let's go ahead and find that. If I want to know the tangential velocity, but before we do that, let's do this. That is the tangential velocity. It would look like a vector like this. So this would be the tangential velocity. We want to know what it is, so we're going to do that. We're going to take 2 times pi, and then we're going to take that times 5. 5 times 2 is 10, times pi would be 31.4, and we're going to divide that by 10. So if you look, I kind of made the math easy. So this is 31.4 divided by 10, and that will give us 3.14, and then we're going to call that meters per second. And so that's our tangential velocity. That's how fast we're going at this point. And that's also our speed at that point. Our speed at this point is also 3.14. But our tangential velocity here, let's call this up, okay? Let's call this side down. Let's call this side right. And let's call this side left. So if I'm at point letter A, okay, what is my speed? Well, my speed is 3.14. We already found that. The question is, what is my tangential velocity? Well, it would be 3.14 meters per second, but then I need a direction. So what direction am I moving if I'm at A? So which direction am I moving? Yes, that's correct. I am moving up. So this would be 3.14 meters per second up, and that's what gives it the velocity. At letter B, we're going to say VT is equal to 3.14 meters per second, and then that would be left. Yeah, so this would be left. If I was at point C, our tangential velocity, our VT, would be equal to 3.14 meters per second, and then this one would definitely be down. So that one's pretty easy to do. Finally, if we're here and we have our tangential velocity, VT is 3.14 meters per second, and it is right. So I know some of my students were like, that's really weird. And we never, I don't think we really ever went through it like this. But what's cool is you can see how the speed is exactly the same at each one of these points. The speed does not change. However, the direction does. So you're going to notice that in each one of these, we have a direction that is different than the one before. If we thought about what degrees they were going, we could also do that. But here we're going up, then left, and oops, sorry, then left. This one is down. I guess I underlined the descriptor there. And then this one is right. So hopefully that gives you a little bit better insight into the difference between speed and velocity. And you can kind of see it here a little bit better too. So that's something I'll have to do in class next year, and that'll help. Alrighty, so now let's talk about the acceleration that you would experience. If I am starting, let's do this again. We're just going to do each one of these. And instead of up, down, left, right, let's do north. Let's do south. Let's do east. And, well, that was bad. North, south. I'm tired. East. And then over here, we're going to do west. So let's get rid of what we've mistakenly done here. And then we can get rid of this guy over here. All right. Okay, now I feel better. So let's talk about acceleration a little bit. The only equation on your AP Physics 1 equation sheet for the acceleration of a circle, so AC, which really means centripetal acceleration, that is equal to v squared all over the radius. So let's do our radius again. We're going to go from here over to here. We're going to call that 5 meters. And so that is our radius. And let's say that we are moving at a speed, okay, of 10 meters per second. We want to know what is the centripetal acceleration. So that's this. Now, we're not talking about acceleration that is going in the same direction as the velocity. Instead, we're talking about the acceleration that points towards the center of the circle. So the red line here is our centripetal acceleration. The green line that we have right here is our tangential velocity. So that is the difference between the two. Alrighty, so now we can find out what our tangential velocity is. So we're going to do 10 squared, and we're going to divide that by 5. So that is 100 divided by 5. So here our centripetal acceleration is 25 meters per second squared. Now, the cool thing about this is it has a direction. And a lot of us would say, well, if this is 10 meters per second north for the direction of velocity, then shouldn't we have an acceleration of 25 meters per second squared north? No, we don't. And it's because this acceleration is going to be different. Uh-oh, somebody just said, wouldn't it be 20 meters per second squared? Oh my goodness gracious, you are absolutely correct. Hey, way to go. That's what I need, is I need people to check. Thank you very much. It is 20 meters per second squared. I cannot do math tonight. I'm so sorry. All right, so this is 20 meters per second squared, and that is our centripetal acceleration. That's the one pointing to the center. Our velocity here is 10 meters per second north. Let's say that we go here, and we now have a velocity, and the tangential velocity here, instead of 10 meters per second, let's say it's 20 meters per second. So what I'd like for you to do is tell me, what is the new centripetal acceleration? So what is the new centripetal acceleration? We still have a 5 meter radius, but now we have a 20 meter per second. So I've already seen somebody give me an answer, which is awesome. So we're going to take this, we're going to make it 20 divided by 5. But remember, on top, this is 20 squared. So let's make sure I can do this right. 400 divided by 5, and that will give me 80. Very good. Okay, so I should have had you guys do it for me before too. 80 meters per second squared. Now, we know that this is going to the west, but our acceleration is still to the center. Our acceleration that we had here was also to the center, okay? And so that's the interesting thing. I sped up as I went here to here. My acceleration got bigger, but notice my centripetal acceleration is always pointing towards the center. Okay, cool. So that's acceleration. Now, there's one other thing we have to worry about with acceleration. We're doing this as if it is constant, or we have one acceleration at one point. if we are saying that the acceleration is changing all the time, we're going to change this equation. We're going to leave v squared over r, but then we have to remember that v is equal to 2 pi r over t, the period. So let's plug this in for v squared, and then we'll say that if you change r or t, you're going to change that velocity. When you do that, you change the centripetal acceleration. If you plug everything in, so let's take this and substitute it in, we've got 2 pi r, and we're going to square that whole thing, and then that's over t. So that we just put this right here into just the v squared part, and so that's t squared all over r. Now I'm going to go ahead and square everything on the inside. So this is equal to 2 squared pi squared r squared over t squared over r. I can get rid of 1, 2. I can get rid of the r. And now I'm left with 4 pi squared r over t squared. So now I have a way, if I want to find out the acceleration, and I've got this and it's not a constant velocity, which means I'm probably changing radius, which changes period, then you'll see that, and it'll kind of go through that way. So that is the other equation for centripetal acceleration. So there's actually two. The only thing that's on the equation sheet is this. Everything else that you see here is not on the equation sheet. So you've got to make sure that you know those. You can get them off the equation sheet because we know that c is equal to 2 pi r is on the equation sheet. We also know that v is not on the equation sheet. However, we do know that velocity is equal to change of position over change of time. So a lot of those things will just kind of naturally come because you have to solve for those. And so that'll help a little bit. All right, so let's do force. For force, the force that we have is what we sometimes refer to as centripetal force. And you can say that, so centripetal force. And all that means is it is an inward force. Okay, but here's the deal. There is no such thing as a centrifugal force. That is totally never ever anything that you want to use. There's no force, okay, in a circle that pushes you out. You feel like you're getting pushed out, so you think that there's a centrifugal force, but we don't ever use that term. Instead, we're going to use the centripetal force, which we know is a fake force, but it's there. We just don't call it centripetal. So let's say that you are standing on the inside of a space station. Okay, so this ring is in space, and you are standing on the inside so that you can breathe. And I want you to tell me, what is the force if this thing is spinning? Okay, so we'll say it's spinning counterclockwise. What is the name of the centripetal force? Because it's not really centripetal force. So got one person who said something. Yep, there's two. All right, you guys are on it. So this is definitely starting from the floor, moving this way, and it is the normal force. Okay, let's say that there's another person who is in the center, okay, and they're holding on to a string. And when they hold on to that string right here, that string then is being pulled tight. So what is the centripetal force that is pointing in this direction? Yeah. So this would be the force of tension, okay? So that's really cool. This person also has this coiled thing attached to them. Don't know why it's attached to their head, but it is got a little headband on here. What kind of centripetal force would this one be? So this one I know we haven't talked about in my class, but there is a force here if you have it, and it would be the force of a spring. And what's cool about that is as this spins, you can kind of change that force. So you can make it bigger and smaller, and that can make things super complicated. But we won't do that. We're going to just kind of keep it the same here. All right, awesome job. Let's think about the equations for centripetal force. So I know from the AP Physics equation sheet that the acceleration of something is equal to the sum of the forces, all over the mass. So that's really easy. But what is the centripetal acceleration, centripetal acceleration equal to if we do forces? Well, it is also equal to the sum of the forces, but those forces in the center divided by the mass that is being drawn to the center. So let's go ahead and let's make it look like this. Sum of the forces is equal to MAC. And we said that the sum of the forces then is also equal to M times V squared over R. Now, if you remember in that last equation, we said that V squared over R, or AC, can also be something else. So we could also say this is mass times 4 pi squared times R all over T squared. So here is another kind of funky equation that you could derive if you needed to find the tension of something. So let's say that this circle, okay, I'm sorry, this is not tension. This is the period. So let's do it this way. Let's say that the sum of the forces, and we're just going to look at, let's get rid of some stuff here. Let's get rid of, and so we're not using tension a bunch, let's just use this right here. And let's say that the mass of the person, so the mass of the person is equal to 50 kilograms, alrighty? So that would be our mass of the person. And the other thing that we know about this is, let's say that the normal force from the spinning of this thing is equal to, I don't know, let's say 2,000 newtons. So we have a normal force of 2,000 newtons. We know we have a mass of 50 kilograms. So let's do a sum of the forces equation for this. What is the only force that we have working here? Well, it's the centripetal force, but got to remember it's Fn. So Fn, okay, so we said sum of the forces is equal to mv squared over r, which is equal to m times 4 pi squared r over t squared. So now the sum of the forces is Fn, and that is equal to m times 4 pi squared r all over t squared. And so we know the normal force is 2,000. We know the mass is 50. Our radius, let's give it a radius. Let's say that the radius goes from here to here, and let's say that it's 25 meters. So the radius is 25. We're going to put in 4 pi squared times 25, and then we're going to divide all that by t squared. So I'm going to give you 1 minute, okay? And in that 1 minute, what I would like for you to do is I want you to solve for t squared. Tell me what the period would be for this object if we have all those conditions. So I'll give you a second to do that. I got to pick up my calculator that I dropped on the floor. There we go. Okay, so now I'm back. Ooh, somebody's got an answer already. That's awesome. Okay, so thanks, Joe, for rooting for us. That's awesome. So we're going to take 50 times 4 times, at least Joe's honest, 3.14 times 3.14. And yes, you can just use 3.14. You don't have to hit the pi button if you don't have it, or if you're too lazy like me. And then we're going to take that and we're going to divide it by, okay. So the person that had the answer just changed their answer, which is absolutely fine. We're going to divide that by 2,000. Oh, yeah, I see what you did. Very good. So I had somebody tell me that the answer was 24.67 or 24.65 or somewhere around there. They just hadn't squared their answer yet. So now they're going to take, the square root the answer. So the square root of this is 4.96 or 4.97. So very good. That is exactly what we want. So we know that the period of this is 4.97. Yeah, that's it. Seconds. Okay, good. So 4.97 seconds. So it would take about 5 seconds for this to go around. That'd be pretty quick. The question is, how quick is it? So we can find that very easily because we know that the tangential velocity is equal to 2 pi times the radius all over the period. We just found the period, so let's figure it out. That's equal to 2 times pi times our radius, which is 25, and then we're going to divide that by 4.97. Let's find out what that is in meters per second. So we're going to take 2 times 3.14. Ooh, Zach is on it. 31.6 times 25. We're going to divide that by approximately 5, 4.97. And yep, that's what I got. I got about 31.8 or so meters per second. So this is 31.8 meters per second. The question is, how fast is that in miles per hour? So what I'm going to do is I'm going to go to Google really quick and type in 31.8 meters per second to miles per hour, and we end up with about 71 miles an hour, which I think you could take, although that might give you a pretty high g-force. Okay, so we could find out what that acceleration would be, so we might as well do that since we're already there. We know, well, no, we won't do that. We'll go on, do something else. All right, here we go. Sorry. Okay, so let's do an actual problem. I think this will be super helpful. At least I hope it's going to be super helpful for y'all. This is a really good question. So this one has to do with a centripetal force apparatus. What is that? That is a glass tube that has a string through it. One end, there's mass or a weight. On the other end, there's a mass that spins in a circle. And you have to kind of get it to go. So once you get it going and you're using that little bit of force, then we can kind of get it going in a circle. So that's really great. So here, this experiment is conducted with a 5-gram stopper. Now, you got to think right off the bat, wait a minute, I can't use grams. So I've highlighted that word. And because I can't use grams, I know I've got to convert it to kilograms. But we also know that there are 1,000 grams, and that's equal to 1 kilogram. So if I need to convert this, just know you've got to divide it by 1,000, okay? So if I want to go from grams to kilograms, I got to divide by 1,000. So this 5 grams is exactly what Zach just said, which is 0.005 kilograms. And then I have a 20.2 meter radius circle. That one's cool. And then I have a 50-gram increment, which means that I'm increasing the weight hanger by 50 grams. So that is 0.05 kilograms. And that is the mass of the hanger. This is equal to the mass of the stopper. So now we've got everything we want. We have a velocity, tangential velocity of 1.2 meters per second. Cool. They want us to write a physics equation. So how in the world are we going to write a physics equation? We're going to use the equation that you see here. This number, is it a very big number or is that a super small number? 7.61 times 10 to the negative 16th. Super big or super small? What do you think? Big or small? Yeah, it's super small. And because this is so small compared to the biggest number here, then it's way less than 5%. We can just ignore this little guy right here. Yeah, wow. So that was kind of funny. Yeah, poor Bean. All right, here we go. 7.27. So let's write a physics equation. What in the world? What is the y-axis? So what word do I want to put here? Yes, definitely want to put force. Do I want to put a unit here? Yes or no? Unit on the word force. Do I want a unit? No, very good. No unit unless it's a number. Then I need to put a number here. And the number is going to be the slope. And so we see that it's 7.27, but I need a unit. If you just use the units that are right here, so this one and this one, you'll see that this is a Newton per kilogram. And it's absolutely fine to do that, okay? In fact, that sometimes is easier than having to go through and make that unit something that you're more used to. So we're going to leave it that way. We now need to multiply by something, which is the x-axis label, and just the label itself. So that would be mass, and no matter how you spell it, we'll get it right. So that is mass. And so now we're done because there is no b value that we worry about. We crossed it off. But just because we have it as a Newton per kilogram, you'll have to recognize that there are two units for acceleration. One of those units for acceleration is equal to a Newton per kilogram. If I take a Newton and I make it a kilogram meter per second squared and divide that by a kilogram, notice my kilograms cross off and I'm left with what we're used to, which is a meter per second squared. That's because the gravity or whatever acceleration is a field. So you have an acceleration field, and fields are force per unit mass. At least this field is. They want to know what is the acceleration, so that one's pretty easy, 7.27 meters per second squared, or newtons per kilogram. Either one would give you that. Here's the tough part. Now they want us to know what is the mass of the swinging stopper if the force from the hanging mass is 5.2 newtons. Okay, so let's go through and let's do a free body diagram, or let's just kind of think about what's going on here. They want us to calculate the mass of the swinging stopper. So that's this guy up here. And we know that the mass down here at the bottom times gravity is 5.2. So we know that mhg is equal to 5.2 newtons. We know that the acceleration is equal to 7.27 meters per second squared. They want us to calculate the mass of the swinging stopper. So if I want to do that, what do I do? Can I just use one equation to do that, or should I have to set up a big equation to do that? What do you think? Do I need to set up a big equation, or do I need to do something different? All right, so I see somebody says I can use F equals ma, and somebody else says we need to use v squared over r. I see somebody say sum of the forces. So let's try sum of the forces. Before we do that, let's do a free body diagram for each thing. So over here on the side, let's do a free body diagram for the weight hanger. And we know that straight down is the mass of the hanger times gravity. Straight up would be the force of tension. And then for this mass, we're going to have the force of tension going to the left. And to the right, we don't have anything. Now, here's the interesting part. If I take a look at this, I'm going to say down is positive x, and to the left, so we'll draw this up here, is positive x. Because we know that the glass tube just changes direction, so it will allow me to keep everything going the same way. So let's do a sum of the forces. Sum of the forces is equal to MAC. That's equal to, so now we have the mass of the hanger, so that'd be mhg minus ft plus, and then we'll just turn this into an ft like that, and that's equal to m times v squared all over r. Now everybody says, yeah, but that m, which m is it? Well, it's the only one that is generating the centripetal acceleration or experiences it, because this doesn't move. It can't be accelerating. But this one up here does. And that's how I know that this mass is the mass of the stopper. So that's something that I think is really important for you to realize. From here, we can just cross off the FTs. Now we know that mhg is equal to the mass of the stopper times v squared over r, which is our acceleration. So at this point, we can just say, well, mhg I know is 5.2 newtons. That's equal to the mass of the stopper times the acceleration. And we said the acceleration is 7.27 meters per second squared. So let's find the mass of the stopper. We're just going to take 5.2 divided by 7.27, and that is 0.72. So here we've got the mass of the stopper equal to 0.72 kilograms. So pretty simple problem to do, I think, as long as you understand what's going on in this. The other thing that might be difficult is you've got to remember that the mass that is rotating, the mass that's moving in the circle, is the one that we put next to the AC. And the one that is pulling down is what the force is composed of, okay? That is making that happen. Oh, shoot. You know what? It says, would I need to square the velocity? I would need to square the velocity, but remember here, this is acceleration. And so v squared over r is really a. So this is equal to msa over r. I'm sorry, msa. That's my fault. Mass of the stopper times acceleration. So here's mass of the stopper, and we found the acceleration. We don't want to square the acceleration. We only if this was v squared over r and we use the velocity. So we said the velocity is 1.2. Now you would have to. But here, because we're using meters per second squared, we don't. And then that gives us this. Does that make sense, someone? I just want to make sure. Okay, good. Awesome. Hey, anytime. All right. Uh-oh. So looks like that's not coming out real well. We'll get it. We'll kind of flip it down and up here. If we need to, we can reload it. Here we go. And so we're going to move this up a little bit. All right, cool. Here we go. Using the new mass and the force of 5.2, what is the new speed of the stopper? So I think, Zach, you were doing speed earlier, so you're good. The new mass and the force, what is the new speed of the stopper? So because we've changed things, we're going to find the new speed. So we said earlier that the centripetal force, the sum of the forces, is equal to m times v squared over r. Okay. Hey, no problem. See ya. And so this is 5.2. We have our new stopper mass, which is 0.72. So we want to find this new speed. So that is v squared over, and then r. So what was our radius? Our radius earlier was 0.2. So we're going to put 0.2 down here on the bottom. So there is 0.2. Now, let's solve for the velocity. And somebody's going to have to pick up the Zach slack here because he was doing it all. So let's go ahead and do the math. 5.2. I'm going to take that and multiply that times 0.2, divide it by 0.72, and then I've got to take the square root of that answer. And I ended up with a number. Yep, that's it. Very good, Abby. Thank you. So that is equal to 1.2 meters per second. So remember, that is the tangential velocity of the stopper. What do we mean by the tangential velocity? Remember, that would be the velocity if it's at this point and it's turning in this direction, which is counterclockwise. That would be the speed right here, okay? If it's not changing speed, to be the speed here, but in this direction, at this point, it would be in this direction, so it's coming towards us, and then this one would be going to the right. So this one would be going away from us, this would be coming towards, this one would be going left, this one would be going right, because remember, it's in a horizontal circle, okay? Awesome. All right, so let's take a look at this guy. We've got, there's 3 more things to do, and then we will be done, and hopefully this will help you as you kind of work your way through some studying. The radius of this, so here's the deal. Roller coaster comes up to the top of the hill, okay? Its speed at the top of this hill, so our velocity, tangential velocity in a straight line is 2.2 meters per second. We know the radius here is 3.0 meters, and the passenger inside, there's only one, so we'll get rid of one, is 60 kilograms. They want to know, how heavy would that passenger feel? So based on that, what is it that's creating the centripetal force? What is it that's creating the centripetal force? So this one, yeah. So we want to know, if we want to know what they feel, it's going to be the normal force. The thing creating the centripetal force is going to be mg. How do I know that? So what I'm going to do is I'm going to draw a free body diagram for this situation. And I know that this is mg. I know that this is Fn. And I know that my circle looks like this. Which of the 2 forces, Fn or mg, is pointing towards the center? Which of these 2 forces is pointing towards the center? Yeah, it's mg. So mg in this case is our centripetal force. But the centripetal force really is a combination of these two. But mg is pointing in that direction. So if that's true, mg is positive. Fn would not be positive. What would it be? It would be negative. Okay? So let's figure out how heavy this passenger feels. We need to do sum of the forces, the centripetal, okay, and that center seeking direction is equal to m times AC. From our diagram, we're going to say that down is positive. Why is down positive? Because that's towards the center of the circle. So I wouldn't even say down. You know what I would say? I would say towards the center of the circle. What is that? And for this one, it is mg, okay? For the next one we're going to do, it's going to be Fn. And it's going to be the same type of picture. It's just going to look different. So here we go. We don't know which one of these two is bigger. We're going to find it out here in just a second. So what is the sum of the forces? We said down is positive. So we're going to make mg positive. We're going to subtract Fn. And that's equal to m times, now they gave us a speed. Because they gave us a speed, I want to put in v squared over r at this point. The mass here, we said, was 60 for the person. Gravity is g, so that's 10, minus the normal force. That's what we're looking for. And that's equal to 60, because that's our mass, times 2.2 squared divided by the radius. And the radius here is 3 meters. You'll see that right there. Now I could have rearranged this and made it so that I put Fn on this side and moved mg squared over r to the other side, but I didn't, and that's okay. So you can just do it however you want to. So this would be 600 minus Fn is equal to, now we need to do the math for this. So if you have a calculator, do this also, because remember, I've already made a mistake tonight, and that's, that's cool. Abby, you are so good. Ooh, Cody, good. Awesome. So now we'll do that times this. We're going to divide by 3. And, okay, cool. So here I got 96.8. To get the Fn to the other side, I add it. Then I have to move the 96.8 to the other side. So Fn here is equal to what you all have, and that is 503.2 newtons. 503.2 newtons. My question for you here is, does this person feel lighter than normal? Do they feel heavier than what they normally do? Or do they feel the same? Okay. So do they feel lighter, heavier, or the same? You can type lighter, heavier, or same. Totally up to you. Yep. I'm seeing one lighter, and I'm seeing one heavier. I'm seeing another lighter. So how do you know? That's the question. Well, our normal force is going to be compared to whatever we get for the weight, which is mg. So let's look at that. Fn is 503.2. We want to know, what is mg? Well, mg, remember, is just the mass of the person, which is 60, times gravity, which is 10. So here's mg, so it's 600. So this one is 600. So they feel lighter because 503.2 is less than 600. Ava, does that make more sense now? Because I know that's one that I think a lot of people don't see. Good, awesome. Okay, cool. So this person does feel lighter. If you think about it, when you go over the top of a hill in a roller coaster, on the top of the hill, not inside, but on the top, you should always feel lighter, okay, if you're moving. Awesome. So let's go on to the next one. We've got just enough time to finish these two, and then your guys are going to be awesome here. At letter B, the rider feels 4 times as heavy as usual. How in the world do I do this? So this would be 4 times the force of gravity. Remember that our rider was 60 kilograms. And so here I want to do 4 times 60 kilograms times 10. Now, why do I do that? Because remember, Fg is really mg, so this would be 4 times mg. So this person feels like they are 600 times 4, which is 2,400 newtons. But that's not Fg. That is Fn, because remember, whatever you feel is your normal force. So our normal force now we know is 2,400 newtons. We know our mg is equal to 60 times 10, so that would be 600 newtons. And we want to know how fast are we moving. So let's draw a free body diagram for point B. So for point B, we know that down is mg. We know that up is going to be Fn. We already see that Fn is really big compared to mg. And we want to do the sum of the forces for this. So sum of the forces in the center is equal to mass times velocity squared over r. So which way is going to be positive? Well, let's look at our circle. So we have a much bigger radius this time. It kind of looks like this. So which one is pointing towards the center of the circle this time? Fn or mg? Which one's going to be positive? Yeah, very good. Fn should be positive. So we're going to put Fn first. If you don't do it this way, you're going to get a really funky answer. It might be negative, and you can't do the square root of a negative number. So that's why that doesn't work out sometimes. So this is Fn minus mg is equal to mv squared all over r. At this point, you can either plug all your numbers in and then solve, or you can go ahead and do some math and do that. I would rather put all the numbers in first. So we know that Fn is 2,400 minus 600 is equal to 60 times v squared. And then remember, this is 13 meters. So this is 13. Somebody has an answer, which is good, 19.7. There's another one, 19.75. So I'm going to do it really quick just to double check that we are all doing this right. So that divided by 60 times 13, and then I'm going to do the square root of that number. Oops, I made a boo-boo. So now I'm going to do the square root, there we go, of that number. And yes, you are right, 19.75. So this is equal to 19.75 meters per second. Excellent. Very good, guys. That's beautiful. Alrighty, last one. Here we go. At sea. Okay, so notice right here that this roller coaster, okay, is upside down. And if you notice, is this a perfect circle? Yes or no? Does this look like a perfect circle? What do you think? Yes or no? No. Does anybody know the name of the shape? Does anybody know the name of the shape that was made for roller coasters? Because if you do a circle like this, if you do a regular, well, that would be bad too. But if you do a regular circle, then that would be really bad. You would probably not survive the roller coaster. So they make these loops. These loops, and it sounds like the word cloth. So CLOTH, okay? And then usually when we do things in geometry, we always give it the last three letters as oid. Yeah, it is a clothoid loop, all right? So clothoid loops are used so that when you go through the roller coaster, you don't get damaged, because otherwise you pull too many G's. So this is a really cool thing. Makes it so that you don't do that. All right, so enough kind of funny stuff here. Let's make our free body diagram. So straight down, we know is mg. And then is straight up the next one we want here? Well, let's think about it. Here's a roller coaster track, okay? And we are inside the circle. If you're inside the circle, which way should normal force point? Up or down? If we're inside the circle, which way should it point? Yeah, that's correct. So we want that to point down. If your dot's not big enough, just make it bigger. So remember, dot's not big enough, make it bigger. So that would be Fn. And I don't know how, based on the speed, I really don't know which one of these two is bigger. So once we figure it out, then we can do some things. They want to know what is the radius of this funky little loop here. And that would be from the center out to where we are, okay? Because it would be slightly less here because it's a clothoid loop. So just remember the word cloth and then put oid and you're set. So this would be kind of like that. Which one is positive, Fn or mg? Which one is positive, Fn or mg? Yeah, both. Good. So they're both positive. Excellent. So now we're going to have the sum of the forces is equal to MAC. So that would be Fn plus mg is equal to mv squared all over r. Is it important to write this down? Is that worth a point? Yes, absolutely. In fact, if you don't put that, it really could mean the difference between a 2 and a 3 on the test, or a 3 and a 4 on the AP test, or a 4 and a 5. So you really want to make sure you get it. Okay, cool. So enough of that. Let's do Fn. Fn is equal to mv squared over r minus mg. I cannot cross off the m, so be very careful because I can't cross it off here. So let's find out what the normal force is on this person. So 60 times 7 squared divided by my radius. Uh-oh, don't know my radius, right? But we do know that the normal force here is 400 newtons. Then we're going to take that and minus mg, which we know is 600. So let's do our math. 400 plus 600 would be 1,000. Now, what did I add? Because I have to add 600 to both sides to get rid of that 600. So that's 1,000 on this side, and that is 60 times 49. So 60 times 49 gives me the big answer of 2940, and that's divided by r. So now I can take r, put it here, put the other on the bottom, and I end up with 2.94 meters. So it's not 3 meters. Remember, this one was exactly 3.0 meters. This one is a little different, okay? It's slightly less, and that's cool. All right, I think now at this point, we're done. And if you notice, Fn here is less than your weight. We said that already. So we drew it like that because I guess we really didn't know right off the bat. All right, does anybody have any general questions or any specific questions about the problems that we did, about anything like that? All right, awesome. Hey, thank you so much for coming out and hanging out with Horner here. For my students, I will see you tomorrow, and we will study, and hopefully that was super helpful. I learned some things from that, especially at the beginning when I started drawing those circles and realized that it's easier to show speed and velocity. So nice job, guys. Talk to you later. Peace out. See y'all. Go to bed. Get some sleep. And we will see you later. Thanks, guys. Bye-bye.